I want to start today with an example of how to work with one of these sort of a Green's theorem type problem. So what's the actual exercise?
Yeah, evaluate the integral C.
The integral over C of
Y dx minus x dy, where C is the portion of the parabola y equals to x squared from 3, 9 to 0, 0.
from 3, 9 to 0, 0.
Yeah.
And that's it?
Yes.
Okay. So how do you do that? Like, what is this asking you to do? So the thing you have to do when you're looking at this is decode what this is. So what is this?
So we're giving a path, right? Y equals to x squared. That's
Yeah, what is the actual exercise that this was built out of? Which section?
The section is 6.1.
Number
27.
It can't be number 27. Am I in the wrong section? Oh, I'm in the wrong section. Sorry. Okay. So what is it? What does this symbol mean? Like when you look at that, like what is that? Oh, okay, now I mean the whole symbol is a line integral, but when I'm looking at this, so the first thing you got to do when you're looking at an exercise like this is untangle what it is that you're being asked to do. Right? So what the first thing I think of here is, okay, I'm looking at this jumble of stuff. There's x's and y's all mixed together. There's some sort of vector field that's happened somewhere, but maybe I don't even need to deal with any of that. Maybe it's enough for me to write down a parameterization of this path. Maybe I can figure out a function that describes this path as a function of t, right? An x and so if I could figure out a way to write x of t and y of t so that I'm traveling along the path from 3, 9, maybe I could start here at t equals 0, and I can end up here at 0, 0 at t is equal to 1. Or if I could do that, then I could just use the fact that I know that dx is equal to x prime of t dt, and that dy is equal to y prime of t dt, and I could just plug everything in and have a t integral to work with instead, right? So the idea is this form is easy to work with after you figure out a parameterization of the path that you're working on. So you're right, it is a line, it's a scalar line integral. Okay, so how am I going to do this? How am I going to make an x of t and a y of t? In a lot of cases, these problems, the hardest part of these questions is figuring out what this function is, right? Where does it need to start? Well, we better start at 3, 9. It told us in the question that we start at 3, 9 and we go this way on the path, right? So maybe I could put a 3 and a 9 right here. And then if there's be a t floating around over here, but when t is equal to 0, I'll make sure that x of 0 is equal to 3 and y of 0 is equal to 9. What can I throw into this so that I land where I'm supposed to land? Well, I could put a 3t right here. That seems like if I started with t equals 0 and I ended at t equals 1, if I put t equals 1 in here, what point comes out? What's x of 1, the way I've written this? 0. Oh, that's good. That would land me at the right x coordinate. What should I put here?
19.
What would y of 1 be if I did that? 8? Ew, that's not right. I'm not supposed to land at 8. Maybe what I can do is I can adjust I really wanted to go from 0 to 1, but maybe it would be more natural to think of t running from 0 to 3. And then I'd have to fix this. What's x of 3? 0. What's y of 3? 0. And everywhere on this path, I'm following this parabolic trajectory, right? I mean, we could double check ourselves. What other points are on here that I better be able to hit? How about 2, 4? 2, 4 is supposed to be on this curve, right? Can I land on 2, 4? Nope. Doesn't work. Right? Problem is, T would have to be 1, but I can't put that here because I have an 8. Oh man. Wow, this problem's hard. Oh, now there's an idea. Does that work?
Like I felt like intuitively the easiest way was to do like x of t equals t and then y of t just equals t squared.
That runs the wrong direction.
And then like just setting.
Oh, you want to set the parameters run backwards
Yeah.
from -3 to
Or I did it from 3 to 0.
from 3 to. Oh. Okay, I guess that, yeah, sure. You want a negatively oriented curve? That works too. X of t. So this is where t runs from 0 to 3. Oh, that's. How am I doing this one? You want this, and you're going to let your t values run from t equals 3 to t equals 0?
Yeah.
Yeah, sure. That works. That does it too. Yep. Absolutely. Yep. I mean, these things are, the point is that any parameterization of this path, anything you can write down that parameterizes this path is going to give you a correct computation of this integral. Okay. And there's lots of answers to how to do this. As long as the important thing here is that when you set this thing up, you set it up so that the orientation is in the right direction, starting from this point to this point. And you might worry, okay, well, I'm going backwards here, but that will be taken care of like once you, because of you're introducing a negative sign because you're writing the integral backwards. Okay, I don't want to waste anything. So let's pick, I don't know, what's the name? I'm going to use this one. I like this one. Let's do this. Okay, so without doing anything else, x of t is equal to 3 minus t. Y of t is equal to 3 minus t squared. Dx is equal to minus dt. And dy is equal to 2 times 3 minus t dt. That's the derivative of y is 2 times 3 minus t. Times -1. There. Don't give me a skeptical look about a negative sign. Don't tell me it's just a negative sign. This is the part that's like the going through the motions part of it of a problem. All the fun part is cooking up the parameterizations and whatnot. Anyway, so after you have this just turns into the integral from 0 to 3 of y, which was 3 minus t squared dt. Oh, sorry, not dt. Dx, which was minus dt plus minus x, so minus 3 minus t times dy, which was minus 2 times 3 minus t dp, and then it's boring. It's just a big polynomial. Right, so the hard part of this, the only hard part of this exercise is remembering how to translate this object into something you can actually compute with. Okay, so the reason that this form is so nice is because there's no dot products to do. It's like already laid out for you what you're supposed to do here. You're just doing parameterize the path, cook up the differentials, and then plug everything in. Right?
So that basically just f dot ds, right?
This is like an f dot ds, yeah.
That's why I was confused. Okay.
What problems is going to set?
This is so if this is an f dot ds, to get this sort of object, this is going to come out of an f dot ds. This is a vector line integral. The other way you could think about this, if you really wanted to, is you could put this back into the form f dot ds, where f is equal to y comma minus x, because that's the m and the n from the original. Like, this is the alternate way of looking at it, is f dot ds, where this is f. I mean, again, this is sort of computationally nice because it means you never have to unwind this definition to, I mean, if you did it this way, you'd have to end up here anyway. So why not just start with this form if you have it available? All right, any other questions that I can answer before we go on? Nothing? Okay. All right. I shouldn't say boring after I write a routine integral down. I should say routine or exercise left to reader.
It doesn't matter which direction we travel. Oh, no,
It does matter which direction you travel.
It gave us 39200.
It gave it from 39200. So whenever you set up your curve, you integrate from the starting point to the finishing point in time. So we went from 0 to 3 in the way I wrote it up. If you chose another parameterization, you might go from 3 to 0. It is an oriented path.
Okay, but it doesn't matter like where.
As long as you get from the starting point to the ending point and you stay on this curve, it actually doesn't matter.
And Green's theorem is a different thing.
Green's theorem is a different thing.
Okay.
Green's theorem is an alternative calculation tool. Now, one thing that does come up here in a problem like this, in fact, I'm going to suggest that there's something I want to know here, which is, suppose I asked you the same kind of question. I have this. I have the integral over c of m dx plus n dy. So I've got some vector function on some curve. And I want to know, does it actually matter how I get from A to B? Like in this problem, we picked a problem where I had this set up where I followed this parabola all the way from 3,9 to 0, 0. So the question I've got is there any way, a class of these problems I can set up where it doesn't actually matter how I get from point A to point B, just I've got some path that gets there. After all, this is motivated by the question of, so the big question is, are there vector fields where the path taken doesn't matter? It does not matter how I get from A to B. So the physical motivation for this is, if I ask you how much work it takes to carry a sack of potatoes to the top of the Empire State Building, it doesn't actually, as long as you're walking on your feet, it doesn't matter what you do. You could go any way you want, up and down 9 times, and then measure, and then say the amount of work. The answer will be the same as if you walk across the United States first, and then walk back, then went to the top of the Empire State Building. It doesn't matter. It's called path independent.
Oh my God.
I mean, I don't know about screen therapy in here, but I guess you guys can yell at me if you really want to, but forever recorded on right. So I guess the idea here is that one of the big questions of things that show up in physical problems a lot of times is that when you compute something like work, if you're doing work in a gravitational field, it doesn't matter how you got from point A to point B. All you do at the end is look at what the displacement was from where you started to where you ended, right? The path itself doesn't matter. And so in that case, the path that you take, the C, if you write down something like the integral of C of f dot ds, in a setup like with gravity, all you care about at the end of the day is the A and the B. The point that you started at and the point that you ended at. Yep. No. No. There's a huge number of non-radially dependent vector fields. Okay. So the idea is, if you have a point A and you've got a point B, and if you travel this way, or if you travel this way, or if you travel in some weird loopy thing, and no matter which way you go, that integral is always the same. The path itself didn't matter. This is an idea called path independence. Path independence is one of the most important ideas in the application of vector analysis to problems in physics and engineering, because many vector fields have path independence, and many really important problems in physics are path independent. Yep.
Before you erase the picture, how did you know that the 9 has to equal 0 and 0?
Oh, I just asserted that they were. In fact, you can come up with a parameterization where this runs from, if you want to have a parameterization that runs from 1 million to 2 million, you're welcome to cook that one up, right? You can set whatever time band you want. I picked 0 and 3 because it seemed natural. Right? This is completely up to you. Okay, so we're going to make this a definition, right? A definition to be the idea that different paths give us the same work integrals. What I want you to think here now is that this is supposed to represent work. So we call why am I writing this little note? It's funny, the sort of things I had students tell me that like it creeps them out when like the chalk gets really small and fingertips get really close to the chalkboard. Like, or that I'm up here with like completely covered in chalk and that grosses people out, or I erase things with my hands, that grosses people out. It's just, it must be just disgusting to, okay, so we say a continuous vector field. A continuous vector field. Okay, now that's a good question. What on earth do I mean by a continuous vector field? Well, I mean, what is a continuous vector field? What would it mean for a vector field to vary continuously? You don't have to give me an epsilon delta definition, but this is an important idea. Polly just throws this term out here. A lot of you guys are, have taken sort of higher level analysis classes. What would it mean for a vector field to be continuous? You're welcome to give it a stab.
Okay.
But then I'm going to ask you to make it intuitively clear what you mean after you give it to me. So
I think I can do it.
do it.
Okay, so for any epsilon.
Okay.
greater than 0
Yep.
In the codomain.
Yep.
There exists a delta greater than 0,
Uh-huh.
such that points within the delta neighborhood in the codomain
Okay.
are within, once you pipe them through F, are within an epsilon codomain.
Yes. Intuitively, what does that mean?
It means that a small region in the domain gets mapped to a small region in the range.
Okay, that is also true. I'm going to make that, so I'm going to lift that up to 1. So that's almost what I'm after here. So you are absolutely correct. So I'm going to actually put that in there. So what you've described, I would consider to be the best intuition for thinking about a vector field as a map from a domain into a range. But I want to think about a vector field as assigning arrows to points in R3, say, right? Can you think of a way to rephrase what you're saying in terms of the behavior of the arrows that are attached to nearby points in R3?
Arrows that are close together in the domain are kind of point in a similar direction, have a similar length, if you will. So like their ends are close.
Sure. So another way of thinking about that in the vector field is if the points that you're attaching vectors to are close, the vectors attached to those points are very similar to each other, right? So if these points are close, the vectors are similar, right? Another way of thinking about it is the vectors vary in a smooth way as you move through the field. There's no hard jumps, like you don't cross a line and all of a sudden you're like, oh, I'm pointing this way now, right? The vectors change, small changes in input give you small changes in output. That's not a definition of continuity that you see outside of the epsilon delta. And even the epsilon delta approach doesn't always make that clear what's going on. The idea with continuous functions is that small changes in the input induce small changes in the output. Controllable input changes give you controllable output changes. Okay? So you should think when I write continuous vector field, you should think it is smoothly varying over its domain. Okay, so there's no hard jumps, there's no asymptotes. Vectors don't suddenly turn into 0, or they don't explode to infinity in length. So a continuous vector field is called path independent. Okay, here we go. Has path independent line integrals. If for any condition simple, piecewise, C1 oriented curves in the domain of F. With same endpoints. Draw a picture. Second. The integral on C1 of F dot ds is equal to the integral on C2. So all we're saying here is exactly this picture. You have a point A and you have a point B for any path, any points A and B and any two paths connecting them that are oriented, which means they go from A to B. If that picture gives you the, so here's one path and here's another path. If that always makes the integrals be the same, then this is a path integral. Or that's sorry, this is path independent. Oh, yes. I need to rewrite it. F has path independent line integrals if for any simple piecewise C1 oriented curves in the domain of F with the same endpoints, the two integrals are the same. And this is actually a quite strong condition because I mean any two endpoints and any two curves, basically. Any different endpoints and any curves must have the integrals be the same. So it's not a feature of particular points, it's a feature of the vector field. The whole vector field is path independent. A and B must be allowed to be any points in the domain of F. That's actually called this a global condition. It's not a local condition. It's a global condition on the vector field itself that is path independent. Okay, so the theorem here is that this is connected up. I kind of feel like I want to give you guys the end game of the story here before walking through all the theory. Does anybody actually know the answer to when a vector field has this? So in a differential equations class, if you've seen this idea before, you've seen it under the name conservative vector field. Is where you would have seen this. An exact differential form. Okay, exact differential form are precisely the things that do this. Does anybody remember what exactness gave you? So we're going to reconstruct, so I'm not going to walk through this the way that Kali does. I'm going to try to build up our intuition for what's going on here, and then we'll say what the theorem is after we discover it. What does it mean to be exact? You guys told me last time what it meant to be exact. What did it mean? If I have something that looks like F is equal to Mn, then we say F is exact if what? I know I'm making you guys dig deep in the 242 well here, or your 244 well. What does it mean for a vector field to be exact?
The partial of Pn with respect to x is equal to partial n with respect to y.
Exactly. Now that looks really familiar to me. In fact, when we were working on Green's theorem yesterday, we saw that equation and we saw that it's equal to something. What was that equal to? This was equal to this thing right here. If I think of F as being M and 0, this object right here was the curl of the vector field, right? We noted that the curl of F was equal to, so curl of F is a vector, and it looked like 0, 0, dm, dn minus, dm, dn, dn dx minus dm dy. Okay, so maybe maybe this is gonna like link up somehow to the idea of curl, right? Because we did Green's theorem and we noted that the Green's theorem integral made a connection between the total circulation of a vector field, which was kind of like going around a loop, and the idea of having no curl, right? Or the curl of the curl, which measured the infinitesimal rotation of the interior, was connected up with rotation at the boundary. So I wonder, just linking back to my differential equations, if there's a connection here between exactness and curl on the one hand, and there was another thing that we knew about exact equations. When you're working in a differential equations class, you're studying exact equations, there's a technique that you use to solve any equation that's exact. What did you know you could do when you had an exact equation? Well, you didn't need an integrating factor. If it wasn't exact, you needed an integrating factor. If it was, you didn't. So what could you do? You could integrate. And what'd you get? You guys remember what, like there was this whole thing about partial integration where you integrate with respect to one variable and then the other and figure out the constants and stuff. So it turns out that in your past, what you were supposed, I'm not trying to say you're supposed to remember this, but you should remember on prompting that one of the tricks that you used was you checked this condition, and if it was equal to 0, it meant you could actually integrate f. It meant that f actually secretly was the gradient of some other function. If this was true, then you could find an f that was that had the field as its gradient, right? This thing is called a potential. So now I got a lot of hope, maybe, that we're going to glue all this together, and that maybe, and since I say maybe because I'm a math guy, so you already know the answer is yes, right? That what's going to happen here is it's going to turn out to be the case that path independence, a vector field is going to turn out to be path independence if and only if it's exact, and that happens if and only if the vector field is actually the gradient of some potential function. It can be integrated to find a solution. And that turns out to be true if and only if the field is irrotational. No rotation in the field, because this is, to be exact, that has to be 0, right? Which would mean curl 0 would tell you that the equation was exact, which would tell you that you could integrate to find a potential. So these ideas are all really deeply linked together. So path independence turns out to be a feature of fields that don't rotate at all. So let's see if we can formalize that. So it's not just me talking with the words. Okay, so here's how it all goes together from a theoretical standpoint. But the idea is that, like, this is a place where you're supposed to see a bunch of ideas from the past kind of all come together. So here's one. So the first thing you do is you say, okay, well, the first thing we can say is path independence is the same thing as saying, okay, well, if I have an A and a B, and I'm supposed to say that if I go from A to B and I go from B to A, that those integrals are equal to each other. Path independent means this is true. F dot ds is equal to the integral of C2 of f dot ds. Well, I could subtract this over. And that's the same as saying do C1 and then do C2 backwards, which means go all the way around this loop. Those are the same thing. Path independence is the same thing as saying that the integral around a closed loop C of f ds is equal to 0. If that's true for every closed loop C, then that's true if and only if f is path independent. That's kind of the trick here. It's like you think about path independence being, well, I can do the same thing which way I go. Subtracting over just reverses the integral like it does when you're doing regular one variable calculus. And so to subtract these two things together is to give you a loop that says do C1 and then do C2 in the opposite direction. Okay. Now we make the big sort of theoretical leap here. That turns out to be true. That is exactly the condition of exactness. So let's look at gradient fields. So suppose that f is a C1 function, say f equals x, Rn to Rn, or to R. So f is a scalar function. This is called a potential. That this thing is a vector field. Make sense? The gradient is a vector. Yep.
But where does potential come in?
Potential. So f is called f. Such an f is called. F is called a potential function. Potential, not like it might be a function. It might not be. This is potential used in the context of physics settings where like we think about potential energy, right? So electric potential or equipotential lines, and like, I mean, it's just a quantity that means something that you take a gradient of and get a vector field out.
So that's f is called.
Any f that looks like this, that we're gonna take this gradient of. Any f that is like this scalar function like this is called a potential function in this setting. Yep.
So to refine my question earlier, in nature, are there any like non-radial conserving field?
I mean,
Or do we just, I mean, I guess the only way to do it those.
yeah. I mean, no. I mean, even a magnetic field is going to look locally radial, right?
Yeah.
So yeah.
Okay.
Okay. So yeah. So we're just thinking about f as being like it's just a scalar function, right? F is a scalar map. And so if we're thinking about it in a problem where we're going to take its gradient to get the related vector field, we call it a potential function, and the gradient field that comes from it is just the gradient of the potential. So f is called the vector field or a gradient field. And it turns out to be the case. Because gradient fields are so highly structured, it's not hard to see that one, I'm defining this in a larger field than just R2 or R3, so we'll leave that alone for a second. And I'll come back to it in the specific case of R2. The big theorem here, that if F is defined connected in this open region, then f is equal to gradient of some other function f. That is, f is a gradient field if and only if integral c f dot ds is equal to. Damn, that's amazing. Look at that. It's a fundamental theorem of calculus. That's all it is. So why does physics work? Physics work because nature uses the fundamental theorem of calculus. That's really what it is at the bottom, right? If nature did not use the fundamental theorem of calculus, it would be really damn hard to study gravity. And this is all this is, right? If you think about the gradient as a derivative, we're saying that, I mean, this is an if and only if, right? So if you can evaluate this vector work thing just by computing this, it's like finding some antiderivative and plugging the endpoints in, and it doesn't matter like how you went from A to B, then you have this gradient field condition. And notice here, I didn't say anything about the path. There's no path here at all. I'm ignoring the path. Who cares how I got from A to B? Plug the endpoints in. Yep.
You say is it vector field or gradient field?
No, I mean, I don't mean or, I mean, they're two names for the same thing,
Oh, okay.
right? So it is a vector field, but if we're being more precise when we're talking about potentials, we talk about the gradient field associated with potential. So here I would say F is a gradient field if and only if F has path independent line integrals for some little function F.
Can you remind me what potential means again?
Yeah, so the basic language here is the following. So in calculus 1, you have the idea of function and antiderivative, right? So for example, x squared and 1/3 x to the third plus c, that's the relationship between the two functions. If you start with a function and you integrate, you get the antiderivative. In the language of vector calculus, if you start with a gradient field, and you integrate it, you end up with a potential function. So the relationship here is that you go this way with d by dx. And the relationship here is you go this way by gradient f.
Okay, yeah, thank you.
Right? It's the same relationship, right? You have this derivative integration relationship that holds in the vector setting. I mean, this is like the power, these are the most useful fields in a lot of cases because you don't actually care. All you really need to be able to do is figure out where f came from, what the potential function was. So now the question is, how do you actually find the thing? I'm going to remind you that there's this technique called partial integration, which is the most annoying thing in 241 and 242. Maybe not 241, but definitely 242. So yeah, let's actually do it. How do you find it? Suppose I give you, I'm going to give you a vector field. Here's F. I don't know. How about YX? There's a cheesy one. Okay, F is YX. Now we haven't talked about exactness yet as a formal thing, but let's actually see that I can find this, the typical approach to figuring out what that F could potentially be is first checking to see if you're working with a gradient field. There is a way to figure out if you're working with a gradient field before you do the integration at all. And remember, it was connected up with that idea of the curl not existing, right? So if we're in two variables, I can actually check to see if a vector field is a gradient field. Is F a gradient field? Which means there can't be any circulation around the loop, which means F can have no curl. I need to check. This has to be equal to 0, but I know what that is for a two variable thing because I took calculus 242 or math 242, and I know that this is equivalent to checking this condition. As I don't know anything. dm dx minus dm dy is equal to 0. I did a whole lecture one time having switched to these and had to like undo it all at the end. But nobody recorded it, so there's no evidence I did that. So is that true in this case? Sure, right? dn dx in this case is d by dx of x minus d by dy of y, which is 1 minus 1, which is 0. Okay, cool, right? That means since dn dx minus dm dy was 0, that meant the curl of this thing was 0, which means there's no circulation around any loop, which means that condition of having path independence is going to hold. But if path independence holds, that thing should have a gradient function. Or potential function associated. It is a gradient field. So the answer to this is yes. F is a gradient field. F is grad F for some F. To which your friendly neighborhood math professor says, okay, go find the F. All right. What do? You say, first you sign. And you say, okay, well, M, if F is equal to the gradient of some function little f, then that means that M n must be equal to fx comma fy. So it means to take the gradient of a function, right? And that means that fx must be equal to m and fy must be equal to n. So if I'm going to undo a partial derivative with respect to x, I have to integrate with respect to x. So that means that the integral of, what it means is that f is going to be equal to the integral of m dx, but we got to be careful because this is a partial integral. What do I mean by partial integral? I mean, undoing partial integration requires partial integration. Partial differentiation requires partial integration. So what is the partial integral of the function y dx? Okay, yx, yeah, that's the easy part. Okay, so yx plus a function of y, a function of y. Because if I took the derivative with respect to x, that partial derivative doesn't just kill constants, it kills whole functions of y. There's some possible unknown function of y running around. Now, from this point, you probably learned all kinds of different approaches to figuring out what the other part is. Like one way to do it is you can take the derivative of this and figure out what the derivative of g prime must be. So this thing right here already, this is f. The problem is you have this, if you took the gradient of this, you should get back, d by df dx is equal to y, right? I've got this damn g of y in there. How am I going to get that out? So right now my claim is that f is equal to xy plus g of y, where I don't know what g of y is. But we also know that the gradient of f, which is at this point equal to y comma, okay, the derivative of this with respect to y is going to be x plus g prime of y. Had better be equal to what I already know the gradient of f is equal to, which is yx. So what is g prime equal to? Oh, g prime of y is equal to 0. Oh, I know what g of y is. A constant. And so the potential function that sits over all the top of this is f is equal to xy plus c. Why are there more than one potential function for the same gradient field? Yeah, there's an entire family of potentials, right? You don't know, just because you know where the potential lines are, which structures the vector field, it doesn't actually tell you what the values of the potentials are. Essentially, if you want to know what's going on here, why there's an infinite family of functions in this case, remember the relationship between gradient fields and potentials is that the equipotential lines, places where f is a constant, and define what the gradient field is, because the gradient field is the field that is orthogonal to those, right? Those heights of these things could change, and it's not going to change where the direction of the gradient field is pointing, right? So if you need some sort of intuitive understanding of what the hell this C is doing in here, the potential field structures the gradient field, but it doesn't actually, it's not related to the values of the potential. Okay, so hopefully this is all just a reminder of something that you've done a million times in the past, and you completely, I'm getting some eye rolls in here. I'm getting some eye rolls. I'm not totally serious about this. The idea is this is not supposed to be a complete walkthrough of how this technique works. So my feeling is that instead of walking through this, that it's probably easier for me to record a quick 15-minute video on how this process works, so that if you haven't seen it before, you can walk through the video, as opposed to, it's just, it's going to take me 40 minutes to do this technique in front of a classroom, right? So if you need to see this, because you do not remember it, or you cannot figure out what the hell is going on with this partial integration thing, this is a technique that you're going to be asked to use in these questions. I'll try to record something so you can watch it, or you come into my office and I'd be happy to explain it at length. It's not really, I don't have time to do it in its full generality, because it's really supposed to be something you've seen. Yep. No. Nope. No, the midterm closes at 6/1. Closes at 6/1. So tomorrow, this is the end of the material that this does not, yes, none of the 6/2 stuff or 6/3 stuff is on the midterm, right? The midterm closes at 6:01. And tomorrow, we're not going to do new material. We're going to open up the floor to questions about what's going on the exam review that I handed out. If people have questions about that, I'm happy to spend as much time talking about that as necessary. I will point out that because I gave you guys the exercises I gave you guys book exercises this time because I realized that there was a searchable PDF of the answer guide to the textbook floating around online. So like you're welcome to, I can't post that, of course, and I'm not even sure it's legal. I'm supposed to tell you that such a thing exists, but since everyone in here already knows it, I'm sure. I'm gonna naively imagine that that you know, you search in College Solutions PDF, that's probably something everyone here just did at some point, like, oh man, I'm so behind, I gotta get this homework done, but I don't have time to do it. I'll just copy College Solutions. I mean, no one would actually do that, but at least I have to entertain the possibility that you thought about it enough to search the book. Anyway, so yeah, this sort of is a technique that I'm happy to walk through, but I don't really have time to do it. And the big sort of the big theorem that I want you guys to know is that like what connects all of this stuff together is sort of the upshot of all of this. And the important theoretical thing here is that these ideas are all connected. F has path independent integrals and we should be careful. So like if I restrict myself to functions in R2 or R3, 2 or 3 variable vector fields now, so that the cross product makes sense. Okay. If that F is going to have path independent integrals, if and only if the curl of F is 0. And in R2, we get the exactness condition. So we go one step further in R2. And that's also, all of this is if and only if F is equal to grad F. So this chain of ideas is all hooked together. Right? And this is this sort of 4 ideas here: path independent integrals, curl being 0, F being a gradient of some other potential function, and F being an exact, you know, this is the same as the saying that F is exact. They're all basically the same idea. This is magical. There's no reason to believe that any of this should happen. It tells you there's something really special about R3. Right? It's a good thing the universe is 3-dimensional.
Is that in R2 applied to the?
And so yeah, you have to restrict yourself. So this is only true in R2 because it doesn't make any sense to check exactness for a 3-dimensional vector field, at least in the setting that I'm using here. I'm trying to connect this up with the people's experience with differential equations and why you even learned that. Okay, the last thing I'm going to say today, and I have no time to say it, so I'm going to give you an idea, which is in the context of all of this, what is an integrating factor of an exact equation? Okay, but what does it do? So you start with some vector field and you check to see if it's exact, and it's not. What that means is that vector field has rotations inside of it, right? The original vector field, if you've got a non-exact vector field and you started, there's rotation happening. So you have some differential equation, you want to solve it, and you've got a vector field that has rotations because it has curl, right? What does an integrating factor do? It gets the rotations out of the field. So you replace it with a different problem. Are you even solving the original problem anymore? Oh, I have this vector field, I get fluid moving, and there's rotation happening. So I'm going to speed it up a little bit over here and slow it down a little bit over here with an integrating factor. So there's no rotation happening, and now I've got a problem I can solve. That seems like cheating, right? I mean, you change the vector field to make it conservative. So integrating factors are a lie, man. Yeah. Anyway, it's the first place where you've seen enough math where I can actually ask you to think about how weird integrating factors are in the context of exact equations, right? Because exact equations literally mean no rotation. So if you put an integrating factor in the vector field, you're saying, I don't want it to be like this speed over here, this speed over here, change some directions and change some velocities and get rid of all the rotation. And now you've got a solvable problem that somehow is the original problem, kind of. So you're using conservative physics to solve non-conservative problems. And there's something kind of strikes me deeply weird about that. All right, see you guys.
this again, because they're like F has path
F has
independent.
path independent integrals if and only if the curl of F is equal to 0.
Okay,
If and only if in the specific case of R2, the
Okay.
equation is exact.
is it because in R2 we still imagine that we're in R3?
Yeah, it's you do that thing where you compute the curl, but
Right.
there's the 0 in the C
Yeah.
slide, and this turns out to be that third component of the curl.
Yes, okay, thank you. Can I turn on the homework on the iPad?